Okay, so let's start. We'll talk today about sample complexity and an object called Rademacher averages, which makes life often easy, not always, but often easy in terms of understanding a complexity of a class of functions. So let me remind you that last time we looked at a particular algorithm, and one can say that this is what people are often using. They decide on an architecture or a class of functions, F. Think of these as neural networks if you wish, and then just minimize empirical fit to data, right? So we call it ERM, empirical risk minimization, over a class F. So empirical risk minimization is always with respect to some class F. It cannot be all functions, but it's some restricted family. And we're minimizing our empirical fit to data. And the question is, when is this a good idea? When is this an okay thing to do? And what we've seen is a simple sequence of inequalities, which says that the out-of-sample performance of the empirical risk minimizer averaged over the data set S, although we could make this statement in high probability if we wanted to, so there would be no expectation, and instead it would be high probability over the draw of the data set S. Let's do everything in expectation because it makes life simpler. The expected out-of-sample performance of ERM versus the best in class. Okay? And we're hoping that this is small, which is a limit of our method, right? We're not going to be doing better than the best in class because we're using that model. And we're hoping that this is small. So this difference is at most what's called sometimes generalization error, which is the expected out-of-sample performance of ERM minus the in-sample performance of ERM. Okay? Now, that's an upper bound because we use the fact that this empirical minimizer is smaller than the empirical minimum of the F sub F, and that there was one inequality there. And then furthermore, because it's hard to study this, now you could study this using stability or compression or some other techniques, and we will do that in a couple of lectures. So we'll come back, instead of this object, we'll come back here and study this directly. Now, instead of understanding where f hat is or what the properties are, we'll just say, well, you know what we know is that that f hat belongs to f. And so let's just look at the worst possible difference over all functions in f. Okay? And let's recognize that this can be a loose step, and especially if you went yesterday to a lecture by Misha Belkin, this already might be a loose step. So keep in mind that everything that we're doing are sufficient conditions. They're not necessary. And there are other ways of doing things, but this is the classical approach. Okay, so let's go with the classical approach. Again.
Question?
Yes.
So F sub F is
this is the best in class.
minimizer for N, right?
Yeah, that's right. So this is a argmin of L of F over all functions in F. Yeah.
And on the right side, after the inequality, do you want the first term to be L of F hat?
Yes.
Because that would be the same term on the left.
That's correct.
So
Yep.
you could just cancel that. But
No, this is what we're interested in,
right.
and we're trying to get to show that it's small. So we're developing a sequence of inequalities. Hopefully, at some point, one of them will be small.
Okay.
Yeah.
So basically, you're saying L hat of F hat is less than L of F hat sub F somehow. I mean, because the
I mean,
first two terms are the same.
In expectation, you can rearrange things. Yes. Yeah. The whole game, what I'm going to do today, is provide further upper bounds on this object. I will call this uniform deviations because it's deviation of empirical and expected uniformly over f. So for all f altogether, what's the worst deviation? Uniformly. So these are, I'm going to vaguely refer to this as uniform deviations. And what we're going to do today is provide another upper bound in terms of these Rademacher averages. Okay? Now, these Rademacher averages will provide an upper bound which is actually within a constant factor tight. So we're not going to be losing anything in this inequality, as opposed to possibly losing a lot in these inequalities. And now that object, the Rademacher averages, which I will introduce, can be further upper bounded by other techniques, covering numbers, Vapnik-Chervenenkis dimension, and so forth. So really think of this as this linear progression of this is what you want. Let's try to show that this is small. Well, we can't just show it that it's small. So we're going to go to further and further upper bounds. As we go further, they become looser, of course, but might be simpler. Some of them will become simpler to analyze, and then you show that this is small. Right? So that's kind of the goal of understanding sample complexity. Of course, any sample complexity you get here is going to be overly pessimistic, because that will tell you that you need more samples than what you really need to achieve epsilon accuracy. But at least it tells you something. Okay? Questions about this? All right. So what I advocated is this empirical process viewpoint, which is just for simplicity of presentation. Again, let me write this composition as a function g. Right. So x comma y is z, and g is a function of z. And then L composed with f, when f ranges over the class f, that's just going to be our L composed with f. That's the definition. And let me call it G, a class G. I'm gonna try to make it calligraphic, because that looks like a C, but I don't know how to write a calligraphic, because there will be a regular G later on in the lecture. So that's a class of functions. Okay. And the empirical process point of view is the following. Well, think of this as all functions. Okay? And I'm being vague here because you can't really order them in any sensible way. But for any function, now you fix a distribution, fix distribution P on x cross y. Right? That's the problem. That's the way we model the problem. It's a distribution over the data. Having that fixed, there is expected G, or expected loss, for every function. Right? So there is a profile, goes like that, and that's expected G of z, where z is drawn from this distribution. This is the z. Does that make sense? Expectation over z. Don't read into the profile. I'm just drawing an arbitrary curve. So what we're after is this one. That's the Bayes optimum. That's the, call it G star. It's the loss of the best f star, of the best function. However, when you have data, you only see a perturbed version of this curve, right? What you see is some version like that. Okay, and that is so the green one is an empirical 1 over n sum of g of zi, right? So again, for every function g, green is close to the black curve, right? So the empirical is close to expected with some tails, right? So sometimes it's off if you've got an unlucky set of data. But there is no way, in general, to say that all of them are these two curves are close for all the functions. It's just not possible. There are too many functions, right? And one way to see it is that example where you see the data. There will be a function that puts delta points at the data and says 0 everywhere else. It has perfect in-sample performance, but horrible out-of-sample performance, right? So clearly, you can't go with all the functions. So now, the worry when we do empirical risk minimization, as I mentioned last time, is that if this is really far away, then we're going to say, oh, this is the minimum of the empirical risk. That's where it is, right? And we pick this model. But this model grossly overfits, whatever that word is, because the out-of-sample is horrible, right? That's the worry, right? Everyone recognizes the worry, understands that, right? So now the whole game is to understand when is it okay to just go after the minimum of the green curve. And so what we do is we choose that class F. Now, in this language, it's the same as choosing a class G. And think of this as putting a window like that. So we're putting a window. We're saying we're not going to deal with all functions. We're just going to deal with these functions. So that's a G class, calligraphic G. And now, hopefully, this one has two properties. The first property is that the minimum over the class, in terms of out-of-sample, in terms of expected performance, is close to G star, right? Not in this x direction, but in the height direction, right? So this point, which maybe is the minimum, that's the f sub f, right? And this is the loss of f sub f. Hopefully that height is close to the best height possible. How do we do it? Well, we say, okay, images are maybe maybe there is some hierarchical structure, so our model should be hierarchical, and so we choose neural networks, and so we hope that neural networks should do well, right? In general, if you go over all neural networks of a certain architecture, right? Okay, so that's the first property. But the second property should be that we're not misled by the empirical curve. And for that, this cannot be too large. And what we're doing today is trying to understand what it means to be not too large, right? What does it mean to be not too large so that the dip in the green curve doesn't lead you to a completely different function? That make sense?
Green to be close to the minimum.
You want the green to be close to black
Always.
because you don't see the black, you only see the green.
Right.
If they're close everywhere in this on this set, then you know that going after the minimum of the green will roughly go after the minimum of the black, which is good because we're hoping that
So
exactly.
you only want to look at the worst case max at this point.
Yes, so that's kind of a step which could lose a lot, but it's sufficient. Because if I do show that this holds, then I'm safe. Okay. And in particular, I subscribe to the message, if you went yesterday to Misha Belkin's talk, that in these memorization regimes, in the over-parameterized models, maybe this is not the right approach. And we will study a different path from here that might be more appropriate to these over-parameterized memorization regimes with that are more kind of relevant now. Okay, but this is the classical stuff that you should understand. All right, questions about this? Yes?
Why is the word called wide is the range of proportions rather than like where would be, right?
Yeah, I'm being vague, right? There is no way I can this width is not. I'm just hand waving, right?
Why is it like good empirical like proxy for how wide you can find the range of functions?
It's not the range of functions. I'm being vague and saying that if this is kind of how big the class is, whatever that means, then worse is, if it's bigger, then it's worse. The empirical can only get further away from the expected. We will understand this point, but kind of this is actually a good message. So it's not clear what it means to be large, right? And so think of this Rademacher averages as just an X-ray that will tell you how large it is, right? It's just a measure of complexity. It's somehow it's the right measure of complexity because it's within a factor of 2. from what we want. So it's a way to measure the size, which I'm hand waving here. Make sense? Yes?
But it doesn't quantify the approximation.
It does not quantify the approximation. So right now we're hoping, it's only a hope, that we chose a model that closely approximates. Now, if you want to put these two pieces together, you would have to also say how fast this goes to G star as you start increasing it with more data. So now you start balancing approximation error and estimation error.
But I mean, is there like another complexity that you can measure the closeness?
No, because this is really driven. When you decide that you're doing empirical risk minimization, it's very natural that there is a stochastic term, which is just you don't see the actual distribution, you see the random data, how misleading that is. And then there is an approximation term.
So I mean, what you say is data marker is for bounding the first.
Just the empirical, yes. Approximation theory is a different subject, and typically with somewhat different tools.
There will be one class.
There will be one class on approximation theory towards the end. Okay? All right. All right, so that's the kind of the setup. And so the question is, can we get something here that is, for this question mark, that's kind of an object that's nice, easy to work with, right? And note that at this point there is an algorithm, f hat. At this point there is an algorithm. But at this point there is no algorithm. So what we've done, and this is something that we do often in statistics, is we get a measure of performance upper bounded by some purely stochastic object, purely probabilistic quantity. And now we try to go after and understand the behavior of that object, right? We're going to go after this object. There is no algorithm anymore. It's just difference of empirical and expected quantities over a class, right? All right. So without further ado, I will start introducing the relevant quantities. Let's see if I... let me spend actually just one more second on this. So let me look at the expected max over. I'm going to now write it as G in G of expected G of Z minus empirical G of Zi. Okay. So first of all, let me call this variable U sub G. So for every G, that's a random variable because it's a function of a bunch of random variables. Any function of a random variable is another random variable, right? So that's a random variable. And now we have a collection. And this collection is indexed by G in this calligraphic G. Now, the mean of every single one is what? What's the mean of this random variable? 0, right? That's the meaning. The meaning of that is that the green curve is centered around the black curve for every point, right? But I want to convey that I'm going to repeat myself. I want to kind of convince you that the size of G enters the picture. So if G is a singleton, if G is just a single function, then, well, you get 0. For these uniform deviations, there is nothing to do. But now imagine that you have a coin flip. Okay? So you have a coin flip plus minus 1, tails, heads, with probability 1/2. Okay? So unbiased coin. And you have another unbiased coin. And I'm going to look at what is the expected maximum of 2 coin flips. So is that 0? expected maximum of 2 coin flips? Well, let's go through this. There are 4 possibilities. Either they both end up being -1, in which case the maximum is -1, or 1 minus 1 minus 1, 1, in which case the maximum is 1. And the final possibility is 1, 1, in which case the maximum is 1. So in 3 out of 4 cases, maximum is 1. And with probability 1/4, the maximum is -1. So you see, just with these 2 coin flips, you already see that the maximum starts to be significantly bigger than the expectation of the single random variable, right? So that's just another way to try to convince you that somehow the more of these you take, the bigger is this maximum, right? Does that make sense? But somehow, suppose I told you that the coins are exactly correlated. So when I flip one and it's heads, the other one also comes out heads, right? So there's some, metal bar soldered, and whenever you flip one, the other one comes out the same. Then again, the maximum is 0. The expected max is 0, right? So it's not just about the number of them. It's also about correlations. So now the story becomes more murky, because in that picture, it's really not just the size in terms of the number of them, but also somehow how they're related, how they're correlated, okay? And that's what we're trying to capture now. Does that make sense? All right. Okay, so what I'm going to do is rather than thinking about the class G, which is a class of functions, I'm going to think of a subset of an n-dimensional space. So again, I'm going to call it G, but this is a usual G, not calligraphic. And for the next 20 minutes, this is going to be a subset, probably not equal. Well, actually, no. Subset equal to -1, 1 to the power n. Okay? So -1, 1 to the power n is a hypercube, the whole box, in n dimensions. Okay. And I want to understand what is the size of this set. And this is a vague question, but let's see. So what can I do to see how large it is? It's some subset of the cube, right? What can I do? What are the possibilities? First of all, I can count the number of, if G is finite, then I can count. Which is just I'm going to write it as a size of G. But this can be infinite, right? So the set can be infinite. So what else can I do to understand the size? Volume, excellent. So the problem with volume is as one dimension becomes more and more narrow, the volume goes to 0. But the n-1 dimensional volume can be non-zero. So there is a certain unsatisfactory aspect of the volume that it's discontinuous. Once it goes when it gets to the n-1 dimensions, then again it has n-1 dimensional volume. But before that, it's almost 0, right? So it's a good guess, but it's somehow unsatisfactory, right? So let me draw this object. So this is a -1 +1 n times, and this is -1 n times. So this is an n-dimensional cube, and you have this object inside. draw it like this. All right. So that's our G. And now what you want to understand is the complexity of this object G, right? So here's another proposal. I'm going to look at, I'm going to start at, I'm going to mark a 0, 0, 0 here. And looks like a Band-Aid. And I'm going to look at a vector, and I'm going to measure the width of this object in that direction, which I can do. Right? That is, I'm going to project the whole object, collapse it onto this one direction, and just see in one dimension how big it is. Right? And now let me sweep through all the directions and measure that length. So that turns out to be an interesting and nice measure of complexity. How do we write this down? Let's write this down as a. Okay, so what is the projection? Well, I'm going to take a maximum over. Let me call it a. What do I want to call it? Let's say U. Now U is going to be ranging on the sphere, on a unit sphere. So this is a way to write a sphere, S n minus 1. Why is it n minus 1? Because a sphere in n dimension has a n minus 1, really n minus 1 dimensional object, right? So that's a common way to write n minus a sphere in n dimensions. Okay, and what is the length in that direction? Well, you look at that unit direction, and then you, sorry, that's not what I want, sorry. We'll have to erase. I'm going to look at the expectation over U drawn from the sphere n minus 1, uniformly at random. And then I'm going to max over, let's call it G in G, right? So U is this direction, unit direction, and then I'm going to look at the maximum, the projection. Okay? That's just the inner product. So that's a measure of complexity. Think of this as an X-ray. So I'm turning this object and looking, or turning the direction, and I'm looking at the width in every direction on average. Okay? When I write this, what I mean is that it's a uniform distribution on a sphere. Okay? So uniform on the sphere. All right?
So you want the biggest projection?
On average, I want to get this point, right, in that direction. That's the width. So that's exactly the, that's how we write it. It's a maximum over G, right? Maximum, this is the point, and that has the maximum projection onto the U, right? And that measures the width, or at least one directional width, right?
But it doesn't matter like if it's this way or the other way.
I'm going to sweep over all directions at random and average the width in all the directions. So if there is one direction that sticks out, I don't care about that.
No, I mean in a given direction, or fix the direction for now. When you try all the G's,
Yes.
you're going to get different projections.
I'm going to take the largest one. That's the max.
The largest in like the magnitude.
Yeah.
Not like if it's in
It's the largest projection. This is the projection.
that direction, you take that too.
No, because I'm going to take the max. There is no absolute value here. I'm just taking the maximum. So that's a number. I'm going to take the largest. Yes.
Find the element in the set of functions which has, on average, the maximum projections.
So I don't want to think about these as functions now. Let's just think of this as a set. Really, it's just a subset of Rn. Or minus 1 to the n. Yeah. Good, yeah.
So what is going to be the result of this? A sphere that contains this object, this weird shape?
The result is a number. In expectation, what is the? It's a number. I'm going to get a number out. Yes.
Wouldn't the boundary of the hypercube also be
But this is the G, right? This is the G. I actually don't. I mean, if G is equal to the hypercube, yes. But my G is inside of the hypercube.
Right. I guess my question is, does this method differentiate from between the boundary, like all the possible sets that have the same boundary, wouldn't they all project into the same?
That's correct. So we'll get to that point. Yep. That's right. Good. All right.
So do we know what this gives for the square, for instance?
Yes.
Just give one.
Just give me 1 second, and I'll get to that. Yep. Okay. Calculations with that might not be too nice, so I'm gonna replace it with something very close. So that's version A. Here's version B, which is expectation with let's call it a Gaussian nu from a normal zero identity in N, max over G in G, nu G. That's another sensible notion which is very much related. It says draw a random direction from a Gaussian, not from a sphere, but from a Gaussian, which has the same shape as a sphere, right? Because it's a isotropic Gaussian. So you can see that these are very much related.
So you're saying 0, mean, and what?
Identity in n dimensions. Isotropic. Okay. These all make sense, right, as measures of complexity. Now I'm going to give you option C, which is expected max over G in G of epsilon G, where epsilon is, so let me write it like this. Epsilon is a sequence epsilon 1 through epsilon n of IID coin flips, plus minus 1. So epsilon I are IID plus minus 1 unbiased. Unbiased, I mean probability that it's plus 1 is 1/2, probability that it's minus 1 is 1/2. So another way to say it is, instead of doing all the directions, I'm going to sample just the vertices of this hypercube, this very hypercube, and I'm just going to look at the width of this in that direction. Okay? So it seems like you're missing a little bit by doing that, because you're only looking in 2 to the n directions rather than a continuum of directions. But somehow this is the right, or it actually can be related to this one. So before I answer your question, let me just call, this is the Gaussian width. And these are the Rademacher averages. And as you can see, they're not scary at all, right? It's just expected maximum for projection. One question, yes?
The set is convex, can like bound these two.
You can always bound one with respect to another. Convexity of G doesn't come when you relate one to another, but you can relate this to that with some factor, right? So sometimes you can lose a log factor here, but in one direction you get. Maybe we'll do it for the homework. Thanks for suggesting. Yes.
Was that only enough for really large values of n?
For really large values of n.
Like, because then it can probably go into
So the relationship between these quantities can be up to log n factor. So So I don't know how you consider that. Is that better or worse with n? You had another question?
Because like in the directions that you're missing, the object can be like very wide.
It cannot.
Oh, you mean like we see the
Yeah, you would see it.
situation.
Yeah, you would see it. Yeah. Good.
Is there, I mean, we're not bounding the norm of the Gaussian vector here, right? So does that affect the,
This is a standard Gaussian, so it has a certain.
so it
Sorry.
can be
Okay, maybe you might want to normalize it to have a unit length. That's correct. Yeah. Yeah. So the relationship between these would involve that as well. Okay. Let me actually. So one normalization that I do want to do is this is in n dimensions. So I'm going to put 1 over n here. 1 over n, 1 over n. Because once we consider Rademacher averages, that's what we're going to be using, 1 over n. Okay? Actually, no. So this is the right. The scaling is correct. You don't need to normalize by any other dimension. Any other questions? Yes.
Given a particular model, how would you determine like what G
What?
like given a particular model, how hard it is to determine like the G?
The G, yeah. So that's a great question. So the question, at some point, our set of neural networks will become this G, and understanding that shape will give us insights into how many examples you need to learn a neural network, right? That's the idea. But before we get there, let me give you a bunch of tricks, tools, and so forth. Yep. Good. Okay. So we've got a bunch of different notions of complexity: count, volume. These three possibilities, which are all related to each other in a simple manner. And we're just going to be using this one. Okay. I'm going to be using Rademacher averages. All right. So let me give a name. So Rademacher averages. Rademacher averages of a set G, which is a subset. Now, actually, it doesn't have to be minus 1, 1. I can do it with Rn. That's okay. Are defined as, let me give it a letter, R hat of G, and that is 1 over n expected max over G in G. No, that's a vector G of epsilon G, okay, over epsilon 1 through epsilon n. So these are vectors, of course. From now on, vector epsilon is a vector of independent coin flips plus minus 1. I will also call them Rademacher random variables. So these are the Rademacher random variables, coin flips. Okay, so let's do a couple of things. R hat of a singleton is equal to a single vector. What's the width of the single vector? 0. Okay. What's the width of plus minus 1, the whole cube to the n? That's the question that was raised. All right, so let's go through this. Anyone sees this? So this is the whole cube. Let's see. Not two vectors, but the whole cube. 1, right? So let's go through this. The way to think about this is kind of a sequence of operations. You draw random coin flips. That's a direction. And now you go over the set, which is also the cube. So you would just go with the same point of the hypercube from which the coin flips originated. And that will give you n as a product. And divide by n, you get 1. So that's a bad thing. That means that in the language that we'll be using later, that means that the model can explain anything. And so you might be able to overfit with this. It might be susceptible to overfitting. Yes?
Why is the same as we were supposed to take G to be one of the biases? Then
There is no max. Expectation on average. So you have to use the fact that it's on average. Because you're going to get that or minus that. On average, that's going to be 0. Right? More mechanically, expectation comes in, that's linear, kills this. This is mean 0. So the whole thing is mean 0. Good? Let me define a notion of LP norm. So this is called LP norm of a vector. So given a vector x in Rn, the p norm of x is a 1 over p sum of absolute value xi coordinate raised to the power of p, I from 1 to n. Okay, that's just a way to measure size of x in a different norm. So in particular, an L1 norm is just the sum of absolute values of the coordinates, right? Everyone is familiar with that, hopefully. And let me define the unit ball in n dimensions with respect to p as the set of x's with the p norm bounded by 1, right? Okay. So what does the 2 norm ball look like? Well, that's the actual ball, right? That's the actual basketball shape, right? Okay, so that looks like that. How about b and infinity? So when you have p is equal to infinity, this becomes a max coordinate. So what does that look like? It's the set of points x whose max coordinate is bounded by 1 in absolute value. So that's a cube, a square, right? Looks like that. How about b n 1? L1 ball, it's this shape, right? It's this shape. And it's actually, unlike the other ones, it's useful to kind of try to draw it in more than one dimension, let's say in 3 dimensions, because you start seeing how small it is. In high dimensions, this is actually a very small object. The way that you should think about these is as a bunch of spikes coming out, thin spikes coming out of some kernel in the center, right? So let's see if we can. Let's see if Rademacher averages actually see that as being small. So what's r hat of? Let me actually start with b and infinity. What is that equal to? We already did this, right? It's 1. How about r hat of b and 1? 1 over n, correct. It's 1 over n. So let's see how do you see that. Let's look at this one. So again, it's good to kind of go in the order. You draw random signs. And now you're going to pick the vertex. Now, the maximum of a linear form is always at the vertex. So you just have to check the vertices of this L1 wall. Right? Each vertex is characterized by being a hot 1 vector, right, in the language of machine learning. 0, 0, 1, 0, 0, 0, right? So that 1 should really line up with some plus 1. And if there is no plus 1, well, you would take another vertex that's minus 1 and line it up, and then get 0 everywhere else. So that will give you 1 for this product, and then 1 over n overall. Right? So that's indeed, this is 1 over n. So you see, this is really small. This is impossible. This is too large. And we're going to be playing in between. And we're going to be trying to see where neural networks fall, or whatever your favorite model is, kind of in this range. Okay, let's do another one. How about r hat of b2, bn2? Just the usual basketball, right? The usual L2 Euclidean ball. Well, this will require just a bit more work. So let me write it out. It's expectation over random coin flips, max over a, what letter did I use? G. G in B2n. In other words, I can write it as a norm of G less than 1, the Euclidean norm less than 1, of epsilon vector and G. Okay, what do I do next? It's a little bit more complicated, and so it's useful to know about duality in this case. So what is duality? Well, you give me a norm, I can give you a dual norm, and the dual norm is defined, so given this norm, the dual norm is a, so the dual norm of a vector f is defined as a max over G of the primal norm bounded by 1 of fg, right? That's the usual duality between norms. And it turns out that L1 norm is dual to L infinity, and I can leave it as a homework for you to prove. L2 is dual to L2 to itself. L2 is dual to itself. And in general, LP is dual to LQ, where 1 over P plus 1 over Q is equal to 1. So that's the duality. Okay, hopefully some of you have seen this, at least. So these norms, you start from 1 and infinity. These are dual. And then all of these are dual, all of these are dual, all of these are dual. And then they meet at 2. L2 is dual to L2. And then they go in the opposite directions. Okay? So that's duality. So with this, I think we can resolve the question. So that's exactly the definition of the dual norm, right? Yes? I've just written this down. And we know that L2 is dual to itself. So that is nothing but expected length of the vector. Okay. Again, this is the L2 norm, the Euclidean norm, right? Okay, I went through this because of the homework. Of course, you can solve it without that, right? The maximum over a sphere is the element in that direction, right? So, nope, there is no square. But it's unit, so you normalize by the length. No. Yes, but this is yeah, sure. That G is equal. Yeah. Okay. Okay. So what? Oh, I forgot 1 over n. Sorry. Please put this in your notes. 1 over n. So, what is the Euclidean length of a random vertex from 0? How far is a vertex of the hypercube from 0, from the origin? In n dimensions. Square root of n, right? Square root of n is the length. Does it depend on which one it is? It doesn't. So, in fact, this expectation is useless because they're all the same. So that's square root of n, and then 1 over n, so you get 1 over square root of n. And that's actually the kind of the type of result we would be expecting, 1 over square root of n, right? This is going to be very rare. That's not interesting. And this is impossible. And we're going to be working around the kind of 1 over square root of n type. Okay? Good. Just to help you a little bit with the homework, there's another way to write this, which is useful. What you do is, suppose I didn't know what the length to the vertex is, so let me just do it mechanically. I'm going to square and take square root. I haven't changed anything. Yeah? And then I'm going to push this expectation inside by Jensen inequality. So square root is a concave function. So Jensen inequality, which you're hopefully familiar with, tells you that expectation of a concave is less than concave of expectation, right? Expectation of 2 points is less than the function at the average or whatever, the mixture of those, right? So that's upper bounded by square root of expected norm of epsilon squared. And now this is easier to deal with because now we're looking at, we've removed this pesky 1 over p, and now we're looking at the powers. And of course, this is just n, right? It's a sum of the coordinates squared. The value squared is 1, so that gives you the square root of n again. Okay, so that's a useful step to remember. Okay. Let's see what is the next example. Let's see. Let's do a few more. Let's do a few more. How about r hat of 2 vectors plus a vector of 1s? So that's the all 1s corner of the hypercube. And all minus 1 vector. So what would that be? let's think about this. So it's 1 over n expectation over a bunch of coin flips, max over 2 possibilities, plus vector of 1s and minus, so g is either this one or minus a vector of O minus 1s of epsilon g. Okay, I'm going to stop writing the vector. It's clear. That's correct. So which one are you going to pick? Right? This is just the sum of epsilons, right? That's the sum of epsilons. Or minus the sum of epsilons. So you're going to pick the one that's bigger. But the maximum of the sum and the minus the sum is the same as the absolute value, right? That's the definition of absolute value. So that's the same as 1 over n expected absolute value of the sum of epsilon I from 1 to n. And indeed, when you add up a bunch of plus minus 1s, they behave like square root of n. And 1 over n, you get 1 over square root of n. Right? Okay? Yes?
Is this actually 1 over square root of n? Or
No, yeah, so I should write. Let me write like that. Without the constant. Okay? So, anything you notice with respect to the previous example? So these two antipodal points, two vertices of the hypercube, in terms of this complexity, are as difficult as a sphere. Right? So that's something that you wouldn't get out of volume, definitely, right? You get the same, and I can provide a lower bound as well. You can get this. You get the same complexity. I mean, at this point, it's not clear that this is the right complexity, but this notion of complexity actually doesn't distinguish 2 points from a sphere in n dimensions, which is kind of remarkable. Right.
Good question. Yeah, why do we take the absolute value? I mean,
It's a max of a sum and minus the sum. And that's the same as absolute value.
all right, it's the max. Okay.
Yep. Okay. By the way, the fact that you have a Rademacher averages of a Euclidean ball being just 1 over square root of n, the same as 2 points, the way that it manifests itself in sample complexity, let's say, of neural networks, is that there are really different regimes. You can have a regime where norms of the weights of the neural network govern the complexity, and not the number of not the count of neurons. So the way that those proofs go is essentially a few more lines from this, right? Okay. I mean, it's a bit more, but we will do that calculation. So it's the same reasoning that norms are quite powerful. They can capture the complexity in a way that's not immediately obvious, right? Because the complexity is the same as for 2 points. Okay. So why are we talking about this object? Oh, there's one more. Sorry. Let me just state this. If if the cardinality of G is finite, then Rademacher averages of G are bounded by, again, a constant square root of log cardinality of G over n. Okay. So it's clear that it's an upper bound, but it could be a loose upper bound where we just count the number of points, right? Of course, if G is huge, as you saw with the ball, even infinite, it could still be finite, but this one doesn't show it. So it could be a loose bound. All right, so here is the punchline. How will we use this? Well, let me first draw a picture. So suppose that we have a class of functions now. So this is a calligraphic G. I don't know how to draw it. Class of functions on some space Z. So this is the Z. And functions look like that. Okay, whatever. And you've got a set of data, Z1 up to Zn. Of course, usually they're not ordered in this way, but just for visualization. So out of this picture, I want to produce for you a set G, which is a subset of Rn. How will I do that? The definition of G, the non-calligraphic G, is going to be a set of all evaluations Z1, G, Zn as you vary G over this calligraphic G. Okay, maybe I'm overloading my G. Before G was a vector. Now this is the vector. Okay. Should I use a different letter? Maybe let me use the H so I don't confuse you. H. It's just a dummy variable. H. All right. So visually, I'm going to take one function. I'm going to look at the value here, 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 here. There are n values. That's a vector in Rn. Yes? I'm going to take this function. I got one value, second value, third, fourth, fifth, up to n. That's another vector. So I'm going to go over all functions, and each function will give me a vector of length n, which is the evaluation of this function on the data. Right? Another way to think about this is a projection of this infinite dimensional object. The function is defined on all the points, and we're just going to project it, we're going to restrict it to these narrow windows, right?
So here's
Just to these points.
the number of points.
So that's correct. So this class of functions, which is an infinite dimensional object, gets restricted to n points through its evaluations, and it becomes an n-dimensional object. And that's an object that's much easier to deal with. Z1 through Zn. There is no kernel. I'm just projecting on the actual values. Hmm? Okay, let's leave that discussion. All I want you to understand is that each function gives rise to a vector and of evaluations, and you can think of this as a restriction, maybe not as a projection, but as a restriction of the function to the data, right? So somehow the function outside of the data stops mattering, right? It's only on the values on the data that matter, right?
But the z's are not numbers. Each z is
Z is yeah. So these are images. These are all the neural networks, let's say. And for each neural network, I'm gonna figure out what it says on every image, and that's a vector. And now I go over all neural networks.
Well, I think maybe what I'm asking is similar to what you were trying to suggest, that now the projection is, I mean, what we have to generalize the inner product somehow.
No. So I don't want any structure on this class G. All I'm saying is I'm going to restrict it to these data points. I'm just not going to look at functions on the whole domain. I'm just going to look at the values, right? So maybe restriction is the right word. So in other words, this G, I'm going to write it as this calligraphic G restricted to Z1 through Zn, or projected onto Z1 through Zn.
That projection is okay, but
Yeah.
I mean, the projection on the epsilons is going to be weird now because each Z is.
Yeah. So
by itself.
yeah. So what I think what you're suggesting is, if I give you a class of neural networks, let's say, and I project it onto data, what does this look like? It's not a nice ball or anything, right? And so what we'll do next is give you a bunch of tools to understand complexity of this object. Okay? So what are some of the tools that you in fact, let me do it at the level of G. So if G is a subset of Rn, and let's say F is a subset of G, then Rademacher averages of F are property A, related to Rademacher averages of G. In which way? Less than or equal to, right? Because we go to a bigger set. Maximum is taken over a bigger set, larger. If you take Rademacher averages of C times G, sorry. So what is C times G? You just multiply every element by C. Every coordinate, every element by C, right? So that's like taking that set, stretching it or pushing it out. Okay, so what do you think this is equal to?
You just multiply by C.
Yeah, just multiply by C. If C is positive. If it's not positive, you have to take absolute value. Rademacher averages of G. C. If what did I want? That's another one. Okay, that's the important one. R hat Rademacher averages of a convex hull of G. How do they relate to Rademacher averages of G?
Bigger. Because everything else is inside.
But do we care about what's inside? The maximum,
It's equal.
that's exactly what was mentioned before. They're equal. Because the only thing that matters is the hull, right? The maximum is always attained at the hull. And the one that we will really get to use a lot is the contraction principle. This is a super useful property. If phi from R to R, so it's a function from reals to reals, is one Lipschitz. So everyone knows what Lipschitz function is. Then, what do you think the relationship is between the phi of G and R hat of G? Now, what I'm going to do is I'm going to define phi of G as just a set of set of vectors which is phi of G1, phi of Gn, where G is in G. Okay, this is a super useful property. Before you give me an answer, let me try to motivate it. Suppose that G actually goes through 0, in which case it is a contraction, right? It takes a point, and each coordinate gets squashed closer to 0. So it takes this guy, right, and phi contracts it to something like this, right? So what do you think the relationship should be? At least in that case, well, it's smaller than or equal to, right?
What if it's not?
If it doesn't go through 0, this still holds. It requires a bit of a proof.
No, I mean,
But
phi could be expanded.
if it's one Lipschitz, and it goes through 0, right? Okay, I mean it can behave in a strange way, right? So it could, like it's for some coordinate it can actually expand in a certain region. So you're right. Yeah. So this is still true. No, sorry. If it's one Lipschitz, it cannot expand, right? Sorry. If it's one Lipschitz, just means that it cannot. Any coordinate will get smaller in that sense.
You have a general function
Right. So the way that we're going to apply it is actually with a bunch of phis for each coordinate. So at least a function that coordinate-wise is Lipschitz. This still holds. There is a result. If it's with respect to L2, then it's out there in the literature I can point you to. And with respect to L infinity, we'll actually put it up this week on archive just for reference. Yes?
So if it's like rotates the set, then it should be approximately the same.
That's correct. Yeah. So a rotation shouldn't change. Shift doesn't matter, right? Right. Okay. So this is a very useful. The way that we're going to be using it is phi is going to be a loss function, and we're just going to be able to get rid of the loss function. If it's let's say a hinge at 0, we'll just get rid of the hinge. It's a very useful technique. Okay. So now, I still haven't told you why we're going to be using it with this class, and kind of the key to relating uniform deviations to these Rademacher averages is the following symmetrization lemma. Symmetrization lemma. So the symmetrization lemma says that let G, calligraphic G, is be a class of functions from some space Z to reals, then expected max over G in this set G of expected G of Z minus empirical on the data. Let me remind you, this is the object we're interested in, right? I'm just simplifying the notation. That's the expected loss minus the empirical loss is upper bounded by 2 times expected value. So this is expectation over the data set, Z1 through Zn. And this is, again, the expectation over Z1 through Zn of Rademacher averages of G, calligraphic G, restricted to Z1 through Zn. Okay, so that provides the relationship. So instead of what we're saying is, instead of trying to understand uniform deviations, it's sufficient up to a factor of 2 to understand the geometry of the Rademacher averages, or the geometry of this set, as measured by Rademacher averages. Okay, and moreover, with another factor 1/2, this is also a lower bound. I'm not going to write it down, but within a factor of essentially 4, this is squished. Okay, so you're not, except for a constant factor, you're not losing anything when you go from this object to this guy. So Rademacher averages provide you a tight control on this uniform deviations. Now, what is important is, let me write out what this object is. I'm gonna write this as a. So I'm gonna use a different color so you're not confused. So another way to write this is a 2 expected over Z1 through Zn, expected epsilon 1 through epsilon n, max over G in calligraphic G, 1 over n, sum. This is the 1 over n from the in front of a definition of the Rademacher, epsilon I, G of Zi, I from 1 to n. Why is that the same? Why is that the same? Well, because this is precisely the product between the vector of epsilons and evaluation of this function on all the data points. Make sense? Right. That's just another way to write it. The key is that everything here is in principle observable, computable. Here, we don't know what this expectation is. There's no way we can just go and, well, there are some ways, but we can't just understand this difference because this is unknown to us. We cannot compute this difference. We only know this part. Magically, through this process of symmetrization, we converted it into an object where everything is accessible to us. The data Z1 through Zn are given to us. That's a random draw. Epsilons are coin flips. So in principle, we can compute. If we don't care about computational power, we could compute this object, right? So this is a data-dependent quantity. This is a fully data-dependent measure. And now the game is the following. Use some of those tools to simplify this object conditionally on the data. So you fix the data, and now see how complex this can be, how complex this can get. Let's see, do I have enough time to do the Kolmogorov example? Probably not. So beginning of next time, next lecture I will do that. So just take my word for it that in many cases, within a few lines, you can get a result that tells you about sample complexity of a problem, given properties of the model. Okay.
So this in green, can it be, like, would you upper bound it by something that is independent of the z's or not?
Yeah, exactly. So one way to do it is just to upper bound it independently of the z's, and then this doesn't matter. Yeah, exactly. And that's the way that a majority of data independent results behave. They
How does something cool